Hi, my name is Arasu, and in this video, I'm going to explain how to derive the 5 SUVAT equations using geometry and intuition. First off, what are the SUVAT equations and where do they come from? These are the 5 SUVAT equations, or constant acceleration equations. The S stands for displacement, U for initial velocity, V for final velocity, A for acceleration, and T for time taken. The key idea behind all of this is constant acceleration, and this was known as far back as the early 1600s. Galileo was able to show that in certain conditions, such as freefall, objects experienced a constant acceleration. Now, he was only able to describe this and not really explain why it happened, but a few decades later, Newton formulated his theory on gravity, forces, and motion, and he was able to explain why this occurred. In this video, I won't be relying too much on calculus, but using a more graphical and intuitive approach to understanding the SUVAT equations. So, let's get started. Let's start from the basics first. We'll see how we can go from displacement to acceleration. Say that I'm running along a straight track and someone is measuring my displacement every second. So my distance from my starting point every second. And in the first second, or when t is equal to 1, my displacement was 1 meter. So a point right here. Now when t is equal to 2, my displacement is 4 meters. When t is equal to 3, my displacement was 9 meters. And when t is equal to 4, my displacement was 16 meters. About here. Now, with these points, I can draw a line of best fit that can let me approximate my displacement in between these time intervals. So, say at 1.5 seconds, even though my displacement wasn't measured, I could approximate that. So let's draw the line of best fit. So if we take the same example, you can see that at point, or when t is equal to 1.5, my displacement would have been around 2 meters, a bit more than 2 meters. And I can say that with reasonable confidence without actually having measured my displacement at that time. How can we go from displacement to acceleration? Well, first we need to find my velocity. But how do you know that I'm really moving? Well, 2 key points from this graph. 1, as time increases, I get farther away from my starting point. 2, as time increases, the rate at which I've run also increases. So, in the first second, I only run 1 meter, but in the next second, between 1 and 2, I've run 3 meters. The next, 5 meters, and so on. So, there is a velocity because I am moving, and the velocity must be increasing because I'm running farther every second. So that brings us to average velocity, which is given by the change in displacement over change in time. There is also another type of velocity called instantaneous velocity. You can think of the difference between average and instantaneous velocity like this. If I travel 60 kilometers in a time of 1 hour, my velocity would be 60 kilometers per hour. But I could have been on a freeway where the speed limit is 100 kilometers per hour, or in a school zone where the speed limit is 40 kilometers per hour. So it doesn't really give us any information about what my speed was at any point in time. In most day-to-day scenarios, instantaneous velocity is what we see, or instantaneous speed. Speed is just velocity without direction. So for example, again, with the car, it's better to know how fast I'm going at that moment rather than how fast I've gone since I started driving. Now, average velocity is essentially the gradient. My rise, how far I've traveled, and my run, how much time has passed. So if we take this entire time interval of 4 seconds and the corresponding displacement, here, my gradient would be this. The value of this slope would be my average velocity over 4 seconds. But I need the instantaneous velocity because SUVAT, as you know, needs precise values for velocities, my initial and final velocity and so on. So how can we get my instantaneous velocity? Well, let's see. You can see that at every second my velocity is increasing. So my velocity between 0 and 1 second, which I've labeled as v1, would be 1 meter per second because I've traveled 1 meter in a time of 1 second. Now v2, the velocity between my average velocity between 1 and 2 seconds, would be my change in displacement, which is 4 minus 1 divided by change in time, which is 2 minus 1. And that gives me 3 meter per second. Now, for the time between, my average velocity between 2 and 3 seconds is 9 minus 4 over 3 minus 2, which is 5 meter per second. And finally, between 3 and 4 seconds, it is 16 minus 9 over 4 minus 3, which is 7 meter per second. Now, these average velocities are the slopes between these time intervals. I'll see if I can draw it. It might not look that good. If we take the average velocity between 3 and 4 seconds, it would look something like this. As you can see, the red line, the average velocity between 3 and 4 seconds, is steeper than my overall average velocity. And it is more accurate than the overall average velocity because I've used a smaller time interval. What if I shorten the time interval, say to a half second? I don't have the values, but the slope would get a little bit more tilted and get closer to the point there. What if I shrink the time difference or the time interval to a very small point? So small that it essentially becomes a point. The point right here. A point or a difference so small that it cuts the graph at two very, very close together points. But since they're so close together, you can essentially say they are the same point or one point. And there you have it. Now you've calculated your instantaneous velocity, your velocity at that point. But how that actually happens is more calculus. So let's see how we can approximate my instantaneous velocity using just the averages. For the first second, my velocity appears to be a constant 1 meter per second. So it would look like this, like a line, or it is essentially a line at v is equal to 1, because I only have my data points at 1, 2, 3, and 4 seconds. So I have to assume my velocity is a constant 1 meter per second. Now, when t is equal to 2, my velocity is 3 meter per second. So that would be a line about right here. And if we plot all of it, we get a graph that looks like a stair. But how can we find a line of best fit, or some way to approximate my velocity at every point? Well, okay, we have one other data point here. I know that I was starting from rest when I started running. So when t was equal to 0, my displacement was 0, and my velocity was also 0. Okay, we have that. But there still seems to be a wide range of possibilities. Well, there's one way to narrow them down. Let's say we only have 2 data points, or my 2 averages, between 0 and 1 and 1 and 2 seconds. Now, a line of best fit could go from either end of my highest average. So, like this. If we add the next average at 5 meters per second and have the same approximation cone, you can see that the cone has gotten narrower at the first data point and at the second as well. And if we add our last one, you see that it's gotten so narrow that it's meeting somewhere in the middle of this line. So we can assume that my instantaneous velocity at the halfway point, so at 0.5 seconds, is 1 meter per second. Now, if we had more averages, we could have a better approximation cone and thus get more accurate velocity readings or velocity approximations at each level. But we'll work with what we have. So, erasing all of this. So if we assume that my velocity at 0.5 seconds is 1 meter per second, and at 0 seconds my velocity was 0 meters per second, we have 2 almost certain data points. And if we just draw a line through them, you can see that it's almost, my drawing's a bit wonky here, but it seems to pass at the halfway points of each line segment. So we can use this red line here as a good approximation for my instantaneous velocity at any point in time. Okay, a small clarification. This is still a line of best fit, but my actual data points, like the ones on the displacement time graph, would be at 0.5, 1 and 1.5, 3 and so on, because that is my reasonable estimate for my velocity at that time. So, and that is what we'll use to find my acceleration. Acceleration, like velocity, comes in 2 parts, average and instantaneous. And like velocity, average acceleration is found by the change in velocity over change in time. And instantaneous acceleration, like instantaneous velocity, would be my velocity at each point, which would involve the shortening of the time interval. But as you can see, this line of best fit looks like a straight line. So the gradient is the same at each point. Therefore, my acceleration must be constant, because acceleration is the gradient of the velocity time graph. But let's see if that's true. My first average, which I'll label as A1, is the average between 0 and 0.5 seconds. Because again, 0 seconds is the first concrete point that I have, and 0.5 is my next best estimate. So, change in velocity is 1 minus 0 divided by 0.5 minus 0. And that gives us 1 on 0.5, which is 2 meter per second squared. Okay, so we can see that my acceleration is constant using the values that I have. So on an acceleration time graph, it would look like this. A straight line at 2 meter per second squared. So you can say that I'm accelerating constantly at 2 meter per second squared. So that's how you can go from a data plot relating my displacement and time all the way to acceleration. Now this will be key for understanding how to derive the SUVAT equations without relying on calculus. The first SUVAT equation is v is equal to u plus at, or final velocity is equal to initial velocity plus acceleration multiplied by time. To derive this, let's first look at acceleration. Acceleration, as you know, is given by change in velocity over change in time. Or, in other words, my final velocity, which I'll call v1, minus my initial velocity, which I'll call v0, divided by final time, t1, minus my initial time, t0. Now, this is the average acceleration formula, and we can use this instead of, say, instead of finding the instantaneous acceleration, because acceleration is constant. So the average and instantaneous are the same. We can rewrite this in terms of v, u, and t. We know that final velocity is v and initial velocity is u. So right off the bat, v1 and v0 are, v1 minus v0 would be v minus u. Now, t is the time taken. If I start measuring at, say, 2 seconds and stop measuring at 4 seconds, the time passed would be 2 seconds. Final time minus initial time. So t is equal to t1 minus t0. And writing it out, we get a is equal to v minus u over t. If we rearrange this, we get first v minus u is equal to a multiplied with t, and take the u to the other side, or add u to both sides, depending on how you do it. We get v is equal to u plus at. There you have it. First SUVAT equation, simple as that. This is a second SUVAT equation. S is equal to a half times u plus v times t. Now, to get to this, we'll first need to look at an example to make this easy to understand. Let's say I'm running along a straight track, and this track has a starting point at x0, and I end at x1. These are another variables for displacement, x and s would be my final displacement minus my initial. So write it up here, s is equal to x1 minus x0, how much I've traveled, or how far I've traveled. Let's get back to the example. Another thing that is measured is my initial and final time. So t0 and t1. Now, with these values, I can find my average velocity. Average velocity is given by change in displacement over change in time. So x1 minus x0 divided by t0. And if we substitute values in, so we know x1 minus x0 is my displacement, how far I've moved, which is s. S over t1 minus t0 is the time taken, which is t. So we have t here. And I can represent my average velocity like that. What if I also know, or my initial and final velocity was also measured? So my v0 and v1. In this case, my average velocity can also be calculated by using the average. Well, it would be v1 plus v0 divided by 2. Now we have two different equations or expressions for the same value. I can represent the average velocity as s over t and as v1 plus v0 over 2, which I'll write as v plus u over 2. So I can let these two equate to each other, and we get s on t is equal to v plus u over 2. We can multiply both sides by t, first, let's factor out the half from the right side of the equation. So we get s on t times a half is equal to a half times v plus u. Here we can multiply both sides by t, and we get s is equal to a half times v plus u times t. The third SUVAT equation is s is equal to u times t plus a half times acceleration times t squared. Now to get to this, we need to look at the velocity time graph first. Okay, we have our velocity time graph with initial and final velocity and time markings. But how can we relate this to displacement? Well, we know that velocity is change in displacement over change in time. Or, average velocity. So if you rearrange this, change in displacement is my average velocity times the change in time. And delta s is s, and t, delta t is just t. So we have v average times t. We can represent the average velocity as something else. Like right here, my v average would be my initial and final velocity added together divided by 2. And that's equal to v plus u over 2. So, again, rewritten, you get v plus u over 2 times t. But didn't we just get the same equation as the previous one? This looks similar to something else. This is essentially the form for finding the area of a trapezium. It's equal to a plus b over 2 times h, where, say, you have a trapezium that looks like this. That would be the height. Here I've labeled the base as b and the top part as a. Now this is a trapezium. This also works for the area of a trapezoid, where this is the height, base, and the top part a. But how can we form this graph into this? We can make a trapezium or a trapezoid on this graph using the available points. So a dotted line like that, another like that, and say, there you go, you go. That is a trapezoid. Now if we were to take this and rotate it 90 degrees clockwise, we would get something like this. Here, and I'll label this right angle. It goes here. So the base of this trapezoid would be V1. The whole base here goes here. So this is V1. And the top part here is V0, because this rotated goes here. So V0. Now, the height here would be T1 minus T0, because that's this length here, and that's translated to here, or here, yeah. So this is T1 minus T0. And if we substitute our known values for V1, V0, T1, T0, we get trapezium or trapezoid with T, U, and V. What we proved here is that the area under a velocity time graph is equal to the displacement. You could have proven this using calculus and by integrating this line here, but this just flows better. This seems more intuitive than learning calculus and going from there. So now we've proved that the area under a velocity time graph is given by this. The area under a velocity time graph is equal to the displacement. But this just gives us the same equation as before. So how do we get ut plus half at squared? We need to look at this trapezoid in a different way, as a triangle and a rectangle. So let me draw a solid line. I've erased my working out here so I could have more space. We have a rectangle. We can split this area up into a rectangle, and a triangle. And I'll label these as such. So area of the triangle, this is AT and AR. Now we can find the area of the triangle by using a half base times height. Here we have a half. The base is T1 minus T0, and that is of course T. So we have T here, times the height, which is V1 minus V0. So write that out, V1 minus V0. using the SUVAT notation, SUVAT, we get half times t times v minus u. Okay, let's see how we can show the area of the rectangle right here. Area of the rectangle is given by, well, base times height. Our base here is again t1 minus t0, which as we know is t, times the height, which is v0. And v0 is our initial velocity, which is also represented as u. So t times u, multiply them together, you get ut. But this still doesn't look like a half at squared. This is where acceleration comes in. We know that the average acceleration is given by change in velocity over change in time. I can write my change in velocity as my final velocity minus my initial velocity. So this is v1 minus v0. And delta t, or change in time, is t1 minus t0. And I'll just write that as t. And the average acceleration is equal to the constant acceleration, so we can just write that as a. Now, v1 minus v0, again, can be rewritten as v minus u over t. If we multiply both sides by t and switch the equation around, we get v minus u is equal to a multiplied by t. And we can substitute that, or at, for this v minus u here. So let me rewrite the area of the triangle. Now I've just rewritten as the area of the triangle above the area of the rectangle, just to make it easier for the working out. So, like I said, we can substitute a times t into v minus u. So we get a half t times acceleration times t. And expanding it out, we get a half at squared. So we know that the displacement is equal to the area under this velocity time graph, and the area under the velocity time graph is given by ar plus at. So let's write that out. S is equal to ar plus at, and if we substitute our values for ar and at, we get ut plus a half at squared. The fourth SUVAT equation is S is equal to Vt minus half At squared. Now you might notice that this looks pretty similar to the previous one. That's because it is. It uses the same approach as the first one, but in a different perspective. We have the same velocity time graph and similar initial and final velocity and time markings. But here, where we took the trapezium under the graph, or the full area under the graph between t0 and t1, in this case, we take this rectangle. Now we know that the area under the velocity time graph is equal to displacement. And we can find that area by taking the area of this big rectangle here, so AR, and subtracting the small rectangle from it, minus AT. And that gives us the area of the trapezium under the graph, which is the displacement. So what are these areas? What's the area of the rectangle and triangle? Well, area of the rectangle is base times height, and our base here is t1 minus t0, which is the time taken, so t, multiplied by the height, which is v1, and we take the full height here. So, and v1 is v, our final velocity. So I'll write it out here, so v1, which is t times v, which is Vt, that's AR. Now the area of that triangle there is equal to, well, half base times height. Here, the base, again, is t1 minus t0, or this length. that length there, so which is t1 minus t0, which is t, so t times the height, so this length here, which is v1 minus v0, so the same as this rectangle here. Yeah, so let me rewrite that. Now since the area of this triangle is the same as the area of this triangle, we can let this equal half at squared because they're the same area. So we get half at squared, area of the triangle. And now S is the area of the rectangle minus the area of the triangle. And if we plug in these values, we get S is equal to Vt minus half at squared. The fifth and final SUVAT equation is v squared is equal to u squared plus 2as. Now this, I feel, is the least intuitive of all five because we get it from using the first two SUVAT equations. So these equations, v is equal to u plus at and s is equal to a half u plus v times t. What we want to do is eliminate the time variable. So let me write out the first two SUVAT equations again. V is equal to u plus at and s is equal to a half u plus v times t. What we're going to be doing here is rearranging the second equation and essentially solving for time. To solve for time, we need to, well, multiply both sides by 2. Let me rewrite that. 2s is equal to t times u plus v. To solve for t, we need to divide both sides by u plus v. So we get t is equal to 2s over u plus v. Now, since we got a substitution or another value for the time variable, we can plug that into our first equation, which is not v is equal to u plus uat, but v is equal to u plus at. We would get v is equal to u plus a times 2s over u plus v. And if we expand this out and write it, we get v is equal to u plus 2as over u plus v. To get rid of the u plus v here, we multiply both sides of the equation by u plus v. So we get v times u plus v is equal to u times u plus v plus 2as. If we expand this out, we get v squared plus uv is equal to u squared plus uv plus 2as. Since we have uv on both sides of the equation, we can subtract it out. So we get v squared is equal to u squared plus 2as. So there you have it. That's all 5 SUVAT equations and their geometric and intuitive derivations. That's it for this video. Thanks for watching Absolute Zero Science, and I'll catch you in the next one.